Okay, welcome to Level 1 Science Online with Henny van Vieren.
Hi guys, welcome to the next lesson in our unit that is all about physics and forces in motion. Today we'll be looking at acceleration. In our previous lesson we looked at how we move from one position to another. That was called motion, and how fast you do that. In other words, your change in distance over your change in time, that gave you your velocity or your speed. Anyway, so today we'll be looking at acceleration. So please join me in this lesson. So you will find these. I've broken down the PowerPoint for you on on the OneDrive. You will find the different ones, and this one is regarding acceleration. Okay, so in this acceleration lesson, we're going to learn up to merit level. I can use the relationship to solve a range of problems involving acceleration, velocity, or time. And our acceleration equation is acceleration A equals change in velocity over change in time. Okay, now remember, velocity is always meters per second or kilometers per hour. So in this case, if we have meters per second, so how many meters that you travel every second, and we divide it by another second, we're going to end up with meters per second squared. Okay, so in other words, it's going to be meters per second squared. Alright, so interpret how an object is moving from shape of its, you need to know how to use the graph and the gradient and calculate acceleration from the gradient and so forth. Okay, so your change in velocity. When something changes in velocity, remember what we said about Newton. He said that an object in rest or in motion in a vacuum will keep on being in rest or staying at that same velocity unless an unbalanced force works upon it. Okay, so unless you have an unbalanced force, things will simply stay the way they are. And consequently, the moment we have an unbalanced force, we have acceleration. So when something is just traveling at 60 kilometers an hour for the whole trip, there's no unbalanced forces on it. But the moment it turns, a change in direction, or a change in how they actually go from 30 to 60, or from 60 down to 30 down to 0, that is a change in velocity, and both of those will be acceleration. Now we talk about acceleration and we talk about deceleration, or a lot of people call it negative acceleration. So from here we changed from 30 to 60 kilometers an hour. That was a positive acceleration. And when you go from 60 down to 0, that is a negative acceleration. Now for those of you who like the triangles, remember that we said that you take the A out, for instance, then we say A equals velocity over time. If it was velocity and they gave you the acceleration, then we could say velocity equals acceleration times time. And lastly, time is going to be velocity over acceleration. So that's your triangle that you are going to use if you choose to. But remember, they do give you this equation at the top of your exam paper. Alright, so acceleration, change of velocity over the time it took. So in other words, a change in time. And that's what this delta means. We talked about that in the previous lesson as well. So a change in velocity over a change in time. Now, if an object is changing speed, and that change is positive, in other words, it's speeding up, we put a plus sign in front of it. If an object is changing speed and it's negative, in other words, slowing down, what the heck, then the object is slowing up. No, it's slowing down. Anyways, then you put a negative sign in front of it. Okay, so positive acceleration or acceleration is always positive. Deceleration is always negative. Now, we've already watched the Felix Baumgartner space jump video. If you want to watch it again, I love this video. I can watch it again and again and again. And maybe you can show your family members just how this guy falls from 40 kilometers up in the sky and lands a perfect landing Yeah, amazing. All right, in your SciPads, you're going to do pages 18 to 19, so please pause this video and get that done. When you are finished, please come back to the video. All right, welcome back. So now we need to talk about velocity time graphs or speed time graphs, and you'll find this information on your site in your SciPad page 20. So the velocity speed graphs, whenever you get a graph, the first thing you need to check is what are they comparing. So remember, we've got rise, it goes up, over run, you run away, so it stays on the x-axis. You're running on a flat line. Rise over run. So what is rise? Velocity over the run is time. So what is the change in speed versus the change in time? So change in speed over change in time. That is acceleration. Acceleration is change in speed over change in time. Change in speed over change in time. And in this case, when we look at the blue line, they go from 0 meters per second to 10 meters per second, and it takes them 2 seconds. So if you go, what is my change in velocity? It goes from 10 minus 0, so that gives us 10, and our change in time is 2 minus 0 gives us 2. So we have 10 meters a second divided by 2 seconds is 5 meters per second minus 2, or squared. Remember that minus simply means that the second is under. So what meters per second? Every second. So I'm going faster, accelerating by 5 meters per second every second. So in the first second I went up to 5 meters a second. In my second I went up to 10 meters a second. Can you see that's 5 meters per second for every second? That's what that means. Now remember, this is not a distance, this is your velocity. Okay, in the red line we can do the same thing. So let's say we go from 0 up to 8. 0 up to 8, and that took us 4 seconds. So we will have a change of velocity, which is 8 in this case, and a 4 at the bottom because it took us 4 seconds. So 8 divided by 4, the rise over the run is going to give us 2 meters a second for that one. Now when you have a straight line, your velocity changes at a constant rate. So we call that constant acceleration. Whenever there's a straight line up, it's constant acceleration. Now the opposite is true when you have a straight line down. In other words, this vehicle or person has gone from 8 meters a second down to 0 meters a second, and it took them from 7 seconds to 10 seconds. So 10 minus 7 is 3. Now, but they started at 8 and they went to 0. So when we talk about change in velocity, so your velocity 2 or your final velocity is 0 minus 8. So it's going to be minus 8 over 3. Because this is constant deceleration, you have to remember that it's going to be negative. That's why we go, it's a minus 8 divided by 3. And if time goes on, like here, this section here, time is moving on, but my velocity is not changing. That means it's a constant velocity. Over here we have a constant acceleration. My velocity is going higher and higher. My velocity is going higher and higher. Over here my velocity is not changing. Remember, your y-axis is velocity. So I'm remaining at 8 meters a second, 8 meters a second, 8 meters a second, 8 meters a second. So that's constant velocity. Again, constant acceleration, constant velocity, and constant deceleration. You're expected to be able to look at them and interpret what these things represent. Okay, so your average acceleration, again, is your change in velocity over your change in time. In this case, it's a straight line, yet again. So we go for 4 meters a second for 5 seconds, 4 meters a second at 10 seconds, 4 meters a second at 15. So that is constant velocity. Then we have, it's going up. So you have 2 meters a second at 5, then we have 4 meters a second at 10, and at 6 we have 15 meters a second. So it's constantly going up, so that gives us a constant acceleration because our velocity is increasing. Over here we're going from 4 down to 2 down to 0, and because the line is straight we know that is a constant deceleration. And the deceleration, if we do the calculation, we go the velocity final, which is 0, minus your velocity initial, which is 4, so that gives us minus 4 over 15. Okay, and so remember to use the start and finish point of the time, the velocity you work out. If the time starts from 0, that is your start point. Okay, so please pause the video and jump on SciPad page 20 to 21. Okay, welcome back. Magic of editing, isn't it? So here was in NCEA, the final exam 2016. We looked at a rocket. The rocket was fired vertically. It left the launch pad, and after, in other words, left the launch pad at 0 time, and after 1.2 seconds it was traveling at 20 meters per second. Calculate the rocket's acceleration. So let's just quickly change this view. I'm going to turn that one off. I'm going to jump here. The rocket was fired vertically, which means it goes upwards. It left the launch pad, and at 1.2 seconds it was traveling at 20 meters a second. So calculate the rocket's acceleration. So we know that, sorry, where's my eraser? So A equals change in velocity over change in time. Now, what is my change in velocity? Change in velocity is always velocity final minus velocity initial, divided by our change in time, which is going to be time final minus time initial. So my final velocity, we said, was 20 meters a second. So 20 meters per second. And my initial velocity, it was standing still, so it was 0, minus 0 meters per second, divided by time final was 1.2 seconds, minus time 0, which was my time initial, wasn't it? 0 seconds. So this gives us 20 divided by 1.2, and that gives us, so 20, sorry, always remember your units, divided, so a meter per second, and if I, so as you can see there, meters per second. So what is that? Okay, so we have 20 divided by 1.2 equals 16.67 meters per second. 16.67 meters per second minus 2, because we added that one, it's another one there. Okay, I hope that makes sense. So let's see what the model answer is. So delta V over delta T, 20 minus 0, that makes sense. 1.2 minus 0, so 20 minus, that gives us 16.67 or 17. No, I don't like that one there. We can stay with that. Okay. So describing motion in graphs. So this is also from a past paper. Describe the motion of the runner through section A, B, C, and D. Your answer should include descriptions and any relevant calculations. So a runner speed is recorded for 25 seconds. You can see. Now, how do we answer this question? Okay, so describe the motion. Let's look at the first part, section A. Section A is basically from 0 to 8 seconds. So from 0 to 8 seconds, this guy went from 0 meters per second and 0 time to 10 meters per second. So that took him 8 seconds to reach 10 meters a second. So that is a constant acceleration because it's constantly going up. Then he remained at 10 meters a second for another 7 seconds, because we take 15 minus 8, because this is our two sections here. So 15 minus 8, that's 7 seconds. And then lastly, he's going from 10 down to 0, and that takes him 5 seconds. But the time is still being recorded, so he is remaining at 0 meters per second, his speed, for the next 5 seconds. So can you see that this section here, he's actually standing still, but it's still constant velocity. Okay, constant velocity of 0 meters a second. And this one over here, section B, excuse me, is constant velocity at 10 meters a second. Over here we have constant acceleration, and over here we have deceleration or negative acceleration. Alright, so make sure that you understand these, please. We are still going to look at this one here at the bottom, and that is when you have acceleration. So in other words, initially not as so, but this is distance time. Remember I told you to always know when it's a distance time graph versus when it is a velocity time graph. So we have to check those all the time. So my distance is getting bigger the longer I go. So that is acceleration. Okay. Now, in 2012, this was a question. A woman drives her tractor down a sandy beach to pick up her friend's boat. The distance time graph shows part of the journey. Use the information from the graph to calculate the average speed of the tractor during the first 90 seconds. The average speed of the tractor for the first 90 seconds. So, what is average speed? Okay, so that's velocity. So we're going to say velocity is, so V equals change in distance over change in time. For the first 90 seconds, so she went from 90, so time final minus time initial, and above the line is distance final minus distance initial. Gives us, so at the bottom we have time final is 90 and time initial is 0, so we've got 90 seconds, and above the line is distance final was, don't worry about that squiggly bit there, because they're just asking us for the whole thing. They don't care about the acceleration at the beginning. If you read it carefully, we're talking about average speed. Okay, so don't worry about that acceleration. First part, so we're at 600 meters, and it took her 90 seconds. So we have 600 meters divided by 90, and I jump back to my calculator, and I clear that, and I go 600 divided by 90 gives me 6.67 meters per second. So 6.7 meters per second. Oopsie daisy, what happened there? Oh. Okay, so there you go. I'm just going to take this away so that you can see the model answer. Okay, model answer says velocity is delta d over delta t, 600 divided by 90, that gives you that. Okay, now pause the video and do the second part where we describe the motion of the tractor section. The motion of the tractor in section B, and it tell us what it says about the forces acting on the tractor. Okay, so please have a look at that. Alright, welcome back. So section B, we're not looking at section A at this stage. So section B is a straight line, and it's a distance time. Distance time means rise over run is going to be velocity. So this is a constant velocity because we are not gaining more, like in this case over here, that's acceleration, so this is constant velocity. And Newton said that if something is under constant velocity, what kind of forces are acting on them? Will they be balanced or unbalanced? When we have constant velocity, an object at rest or at constant velocity will remain at rest or at constant velocity unless an unbalanced force acts upon it. So that's the model answer. During section B, the tractor is moving at a constant speed or constant velocity. This means that the forces acting are balanced. This means that they are equal and opposite. So in 2014, a distance time graph. It's the first thing we need to know. Is this a distance or a velocity time? Distance time. And if you look carefully, we've got three sections. So the question said, the cyclist's journey was plotted on the distance time graph below. The motion of the cyclist in each of the sections A, B, and C. So we need to describe the motion of the cyclist in the first. So section, okay, so there's section A, there's section B. Remember, this is your question paper. You can draw on it as you like to give you clarity. And this is section D. No, it's not. Oopsie. Where's my eraser? Okay. This is section D. Okay. Everybody see? So, for the first 5 seconds, section A. Oh, see, I've given you the answers already. Section A is acceleration because we have it's going up. If it was going down, like here in section C, we call that negative acceleration or deceleration, don't we? Okay, so section A is acceleration. Section B, is the velocity changing in section B? Is it a straight line or not? Yes, it's a straight line, so that is constant velocity. So from here up to there. Then section C, we have a change in our velocity because it is at an arch or at a curve, and because the curve is going downwards, not upwards like here, we know this is negative acceleration and this is positive acceleration. And then lastly, he remains at 19 meters. See that? There's 19. So he remains at 19 for the next 10 seconds. So what did he do? Is he moving if he's remaining at 19 seconds? Or at 19 meters? No, he's not. So he's obviously stopped. Okay. So let's see the model answer there. So section A, increasing speed or accelerating. Section B, constant speed. Section C, decreasing speed. So remember, constant speed means all the forces are equal here in section 2. Okay, so all the forces are equal. And section C, man, decreasing speed or deceleration. And then section D is stop. Question 2 of this says, calculate the cyclist's speed during section B. And we know that speed is, we don't have a delta, we can just say speed, or average speed. So speed equals the change in distance over the change in time. Now if you look at the change in distance, look very carefully. This here is section B. So that's 10 seconds, and this is 5 seconds. You see that? Okay. Now, when we draw this across, and we have to look where this ends. Okay, so what you'll see there is that we basically have our delta D. Now that's change in distance. So our distance went from 5 all the way up to 15. So that means D final is 15 minus D initial, which is 5, divided by, I go from 10 down to 5, so that gives me 10 down to 5 is 5, so we've got 15 minus that is basically 10 over 5, and 10 over 5 is the same as 2 meters per second minus. Okay. Okay, so let's check the model answer for that. So same as what we just found, where our change in distance was from, the distance went from 5 up to 15, and the time went from 5 up to 10, so that's 2 meters a section. Now, what is the total distance covered from 5 to 15 seconds? 5 all the way up to 15. What is our total distance covered from 5 to 15? So if we start at 5, our distance was 5. And if we go to 15, we end up at 19 meters, don't we? So it's quite simple. Our change in distance equals distance final minus distance initial, which gives us 19 minus 5 equals 14 meters. Okay, everybody happy with that? Let's see what the model answer said. The model answer agreed with us. Okay, so that was 2014. Here's 2015. The distance time graph of the rower. So the distance time graph below shows the journey of a rowing boat in a race. Describe the motion of the boat through the journey. No calculations required. Okay, so please pause the video and then on a piece of paper describe the motion of section A, section B, section C, and section D. Can you see how similar this is to the previous one? Yeah. Okay, pause now and please do that. Okay, welcome back. So section A we know is acceleration. Section B, constant speed, because the speed is not changing because there's no curve to it. Section C is deceleration or negative acceleration, and section D is he's remaining at 800, so he has stopped. The distance does not change. Okay, so that was question A. Question B for the same year. During the first 30 seconds of the race, the rower's speed changed from 0 to 8.3. So can you see that this is speed initial? Okay, and over here we have speed final. During this time they covered 125 meters, so that's distance. The total mass of the rowers and the boat is 140. Calculate the boat's average acceleration during the first 30 seconds. So the first 30 seconds is section A, basically. Okay, so what do we know here? We see that we have distance and we have velocity. So we know that acceleration is change in velocity over change in time. We know that the time is 30 seconds. Why did they give us the mass? I think that probably comes in later in the question. Okay, and during that time they covered 25, but we don't need the distance at this stage. So we have the acceleration. So our change in velocity is 8.3 meters per second, and our change in time was 30 seconds. Okay, where's our handy calculator? So that's 8.3 divided by 30 gives us 0.28 meters per second. That is our acceleration. So 0.28 meters per second squared. I hope you can see that. Let's check the model answer. You can see here, ignore this at the bottom please. We have 8.3 minus that, which gives us 0.28 meters per second squared. Excellent. So, the rest of the calculation obviously will come in later. Now this was in 2016, a distance time graph again, and it's a distance time graph. So the graph below shows the motion of a horse. We've done this now many times. Describe the motion of the horse in section A. It's curving upwards. If it's curving upwards, that is acceleration. This is constant speed. This is deceleration, and if the distance doesn't change, it is stopped. Done that. Calculate the speed of the horse and the rider in section B of the graph. So section B is there to there, and there to there. Okay, so please pause and then come back for a model answer. Alright, welcome back. So if we look at this, calculate the speed. So we know that speed is v equals change in distance over change in time, which gives us distance final minus distance initial divided by time final minus time initial gives us, so let's look at this, our distance. We ended up at 500 meters and we started at 100 meters. So that's 500 minus 100 divided by time was 60 minus 30. That gives us 400 divided by 30 seconds equals, where's our handy dandy calculator? Okay, so we have 400 divided by 30, enter, and that is 13.3 meters, no, 13.3 meters per second. Okay, let's check the model answer. Whoop-de-doo, we can't see. Excellent. Okay, so you can see there that it is 13.3 meters a second. Yay, we got that right. Okay, so here we have and this is 2013, but now we have a speed time graph. So why don't you pause the video and take like a 5-minute break or so, and then come back for the second part of our lesson, because we have 2 periods today. Okay, thanks guys for your dedication in this.